Okay, this video is to give a live demo on how to implement the Deutsch problem in IBM Q. I will give a brief introduction to Deutsch problem, but if you want to know the details, you can go to my YouTube channel to look for the details. And all you need to do is just come to here, go to YouTube. Yeah, search for introduction to quantum computing. Right. And you should be able to see my channel here, Introduction to Quantum Computing, or this playlist, Introduction to Quantum Computing from a layperson to a programmer in 30 steps. And if you go down, you will see this channel, this video about Deutsch algorithm, in which I give the details of Deutsch algorithm. Okay. Now let's go back to the PowerPoint. So what is a Deutsch problem in short? Basically, we have a function, we don't know what it is about. It is a Boolean function. A Boolean function means I input 0 or 1, it will give me output 0 or 1. The input can have different length. Here I assume it is 1 qubit. If it gives me a constant output, for example, when the input is 0 or 1, it always gives me 0, this is called constant. Or if it always gives me 1, then it is also constant. On the other hand, if one of the input gives me 0 and other input gives me 1, for example here, if the input is 0, it gives me output 1, the input is 1, the output gives me 0, we call it balance. The question is, can we find out whether the function is balanced or constant quickly, right? So as I said, you can go to the YouTube channel to understand the details. But basically, if you want to do it classically, you need two computations, right? You need to put in 0, find out what is the output, put in 1, find out what is the output, and compare them, then you know whether it's constant or balanced. But if you use quantum computing, you only need one computation. And in quantum computing, in order to implement this, we need to encode the problem, the F, into a so-called quantum oracle, which I won't go into the details. Again, you can go to the channel. A quantum oracle is like this. I have two inputs, X and Y. After this quantum oracle, it will give me an output X and Y exclusive F of X. You see that this quantum oracle does not tell me exactly what F of X is, unlike in the classical computing. But it encodes the answer by doing an exclusive OR with the input Y. So the information are stored there. However, we cannot know the individual answer. This is the flow of the Deutsch algorithm. We will prepare the quantum oracle by encoding the function that we are interested in as a gate. And we will prepare the initial state. Here is a NOT gate, Hadamard gate, as we discussed earlier. But in summary, what we want to do is to create a plus and minus state, or a superposition of 0 and 1 in a special format. Now with this superposition, we pass this wave function into the quantum oracle, in which it encoded the function. So it will do the computation in parallel, but it does not tell you individually the answer of the individual input, but you do it in parallel, okay? And with that, then we do a measurement. In particular, we actually doing a measurement in the so-called plus-minus basis. But don't worry about this. Basically, it's just a special way of doing measurement, and we will use the Hadamard gate if we are actually measuring in the 0 and 1 basis. Due to this constructive and destructive interference, if the output is 0, we know it must be constant. And if the output is 1, we know it must be balanced. This is a very short introduction. But the goal is, if you want to know the details, you can go to the link I just mentioned. And the playlist is also in the comments of in the description of this YouTube video. So in order to implement this, we do this example, right? If you compare to this, you see I have a NOT gate, I have two Hadamard gates, I have Hadamard gate and a measurement. And this is what we're doing. We have a NOT gate, we have two Hadamard gates, and then a Hadamard gate and a measurement. In IBM we swap the layout of the most significant bit and least significant bit. So on the bottom is the so-called MSB, most significant bit. On the top is the so-called LSB, least significant bit, which means that the bottom corresponds to this MSB and the top corresponds to this LSB. But in my drawing, I actually make the top as the MSB and the bottom as the LSB. So you need to be careful when you implement the algorithm on IBM Q. If you get a circuit, make sure which one is MSB, which one is LSB. So that's why you see that I have a mirror image. See, I have the X and H at the top, at the bottom here, but it becomes on the top. This is the NOT gate. Okay? So this is the circuit, but at the same time, I also implemented the oracle. This is a very simple oracle to represent this function, a constant function. Okay, that you will always so in order to understand this, you can think of this, right? If my input x is 0, right? If the x is 0, f of a and f of x, whether it's 0 or 1, always give me 0. So basically this has no effect because 0 exclusive y is always y, right? So as a result, whatever goes in xy will come out as xy, right? So this is just an identity gate. So I use the identity gate to implement this particular oracle. Okay, so because of this, this is a balance, this is a constant function, right? And based on that, I expect to get 0 outputs when I do the measurement. It should always give me 0. Now, this is indeed the case when I do the simulation. Okay, but let's go to the IBM Q, right, to see how to do this. So how do you start the IBM Q? I just go to Google, right, and search for IBM Q, and you just go to IBM Quantum, click on the bottom. So from there, you will need to create a new account if you have not, right, from here. Otherwise, I will just click on IBM ID. So after I click on IBM ID, I come to this page in which I have two portals. One is Launch Composer and other is Launch Lab. Let's look at Launch Composer first. This is a graphical interface and you can build your circuit by just dragging the gate. Okay, so let me just start a new one. So what I will do is that I just refer the first thing. If you look at the circuit, right, the top is NOT gate, the bottom is identity gate. So I start with NOT gate, identity gate, and I only have 2 qubits, so I will right click, actually just click on this, left click, delete it, left click, delete it, okay. And then I need the Hadamard gate. I'm going to click on the Hadamard gate and drag it to here, Hadamard gate, and drag it to here. You can have some separator. The separator basically just, it does not do anything, and it just for the visualization, so you can see different parts clearly. By the way, why do I need the identity gate? I don't need to actually. I can just click on it and then delete it. But then it will go shifted to the left, so it just doesn't look nice. But no problem. But it doesn't matter if you add it, right? So it's better to add it to have a good visualization. So in order to implement the constant oracle, I'm going to drag this identity gate to here. This is the oracle we just mentioned, which give a constant 0 output, and then I will also just add the separator to here, and then to finish the rest. For the rest, I'm going to put the Hadama gate here, and then I will do a measurement, right? So let's double check with the equation, with the circuit I showed you earlier, looks correct, right? Now, this classical bit represents the corresponding measurement you are doing for the quantum qubit. I have qubit 0, qubit 1. This is the least significant bit. This is most significant bit. I only have 2 qubits, so I only need 2 classical bits if I do the measurement. So I decided to just left click and then just reduce it to 2 qubits. So I'm done with my first Deutsch algorithm, and now I can rename it, right? You can call it Deutsch, right? So now let's just go to top right and click on setup and run. I will first run it using the simulator. Okay, just click on one of them, and then on the left bottom, lower right, I click submit the job, and then it will start. It will submit the job, right? And let's wait. It will tell you that it has submitted the job. In the past, it was very fast, but now many people are using it, so it's getting slower. I don't get any response. Let me make sure that it is submitted. Let me just click one more time. Okay, now it says it is running, right? So maybe it was not submitted successfully. So in principle, it should give me notification, but it failed this time. So I click this composer job. Now you see the job I just submitted. I click on it, and I look at the details, right? And then I go down. You see that the output is 0, 0. Okay, now I don't want to, I want to try a real computer. So on the top right, I click on setup. I try to submit to the real quantum computer, and it's good. Not many people compared to earlier I seen. Some of them actually have 200 Q, right? So I don't want to wait for those. Let me try this Lima, IBM Q Lima, and then just submit the job. And I will come to the composer job here, right? This was the old result. I just go up and then go back to this right click, left click the job, and I do have a job that is pending to IBM Q Lima, right? It say it is transpire validating in queue, so it's waiting to run. Let's just wait. Okay, this is not good. Actually, I just paid attention. You say it's going to take 2 days to run. I think the queue is very long. So let me try others. Let's try if we have other machine. Okay, I also try IBM Perf, sorry. It's like 22 days, but the estimation might be too pessimistic. For example, for Nima, now it becomes 5 hours. So I'm not going to wait. I will just show you what I've done earlier. If I go to the job, view all jobs, right? So last night, I actually have submitted a job to IBM Manila, right? So I just click on this job, and which used exactly the same circuit. Now, then this is the output, right? It was submitted yesterday. Now, then you see that besides 0, 0, I also get some 1, 0, right? The first qubit is the most significant bit, right? Let's refer to the setup here. This is the most significant bit that we're measuring. The last one we are not measuring, so we assume it to be 0. So you see that besides getting 0, we also get 1. This is because of the error. Okay, so this is the first thing I want to show you. Now I go back, and then I want to show on the right, you have some script. You see that this is the GUI interface, right? You can do some simple circuit. But if you do some control and also some more sophisticated circuit, you want to modify this into a language. So this is like quantum programming, right? And we can open it in the quantum lab. instead of this composer interface. In this quantum lab, you will find that this is just the same as a Jupyter notebook, right? It imports the necessary library and then it starts creating circuit. For example, remember it created the NOT gate at the qubit 0, identity gate at qubit 1, right? And then Hadamard gate, right? And then I add the barrier, identity gate for the quantum oracle, and then the barrier again, and then the Hadamard gate, and then the measurement. Okay, so if I do shift enter, then it will create this gate for me. Okay, and again, why it's 1? 1 is the most significant bit, like what I'm saying here, MSB, right? So 1, qubit 1, it means on the left. Okay. Yeah, and then you can just add a code to submit the circuit to run it, which I'm not going to do it.